All right, we're going to just graph this one really quick again. If you don't want to watch this one again, just skip ahead a couple minutes and we should be done. But I just wanted to make sure that we got this really well. Okay, original sine curve or cosine curve. So we start with the original cosine curve, completely unshifted or transformed at all. So again, what I want to stress is that the pattern happens in fourths, right? Because if you think about the unit circle, at 0, and then pi over 2, and then pi, and then 3 pi over 2, and then back. So it kind of happens in fourths. So if you think about the cosine curve, it goes in fourths. So it starts at a max. It starts at a max here. And then it ends at a max as well, because the regular cosine curve has its period is 2 pi. And so then what we do is we okay, so it starts at a max, ends at a max. Halfway in between, it hits a min, because, that makes sense that halfway it would, go down and then back up. And then halfway in between each of those, it's going to hit a 0. So that's kind of how I think about this. And no matter how hard I try, I can't seem to get that. There we go. That's a little better. So I think of this as max, 0, min, 0, max, and then it would just do it again, right? Max, 0, min, 0, max. The pattern of the cosine curve. Okay. So then, I guess I know, the math teacher in me needs to finish this so that it's down, so that it keeps going, so that you recognize that it's periodic. Okay, that's not great. All right, so then the 1/2, remember this 1/2 in here with the x is really like 1/2 x, so it takes all of our x values and multiplies them by 2 because it's the opposite of what we see. So we're going to take our x values and multiply them by 2. That x value stays the same because it's 0. But instead of this being at pi over 4, now it's at 2 pi over 4, which is pi, right? So it multiplies it by 2, multiplies this one by 2, multiplies this one by 2, and multiplies, let's see, so we did this one turned into that one, this one multiplied by 2, then this one multiplied by 2, so that's at 3 pi over 4, so now it becomes 6 pi over 4, which is 3 pi over 2. And so that's why that one is there. And then this one at 2 pi, we multiply that by 2 and we get 4 pi. So again, we could have just thought, well, okay, that 1/2 stretches out the period. And so now it's going to go through one revolution in 4 pi instead of 2 pi. So it's going to start and end at a max. Halfway in between, it's going to be at a min. And then halfway in between each of those, it goes to a 0. So we go max, 0, min, 0, max. All right. So we could do min, 0. Okay, so then it would go like this. Okay, so this is the curve so far with just the 1/2. Now we take the -5, and remember the negative flips it, reflects it, I should say, over the x-axis, and then the 5 multiplies by 5. So we're just going to take all of our y values, multiply them by 5. So I'm going to take this point right here. I'm going to multiply it by -5. It goes down here. I'm going to take this point and multiply it by -5, and that's already at -1. So it's going to become +5. This one's already at -1, and it's going to become +5. This one is at +1, so it's going to become -5. This one's at +1. It's going to become -5. And so in the end, this is our final curve. It says an amplitude of 5. It's reflected over the x-axis, and it has a period of 4 pi. So those are all those different things in there. Okay, let's do this one. So the first thing I notice is that this is not in the form that that we have, our standard form, which is a sine b times the quantity x plus c plus d. So do you see how b here, b right here, isn't multiplied by t and a phase shift? So, whoopsie. So it's not multiplied there. So I need to go ahead and pull that 2 out so it looks like this, so that the b is multiplied by the x and the phase shift, okay? So I got to pull the 2 out. So I'm going to end up with sine of 2 times t minus, now what's pi over 2 divided by 2? It's pi over 4. Okay, now I'm in the right form. Right now that 2 is really the b. And if I multiplied it back in, I could see that I get 2t minus pi over 2. Or minus pi over 2. So that works. So I get 2 pi over 4. Okay, so this 2 is my b. And you see that it's inside the function. It's inside the sine function, which means it's going to do something to my x values, not my y values, because it's in the function. And since x lies, I'm not going to multiply my x's by 2. I'm going to divide my x's by 2. Okay? And then the other thing I see is that I see this phase shift here. This right here is, again, inside the function. So it's going to mess with my x's, not my y's. And this one's going to take my x's, and instead of moving them to the right pi over 4 like I would, or to the left pi over 4 like I think it would, it's going to move them to the right pi over 4. Because x always lies. So let's graph the standard no frills sine curve. Okay, so the no frills sine curve starts at 0 and it goes to pi, and then 1, 2, 3, 4. Of course, because of this phase shift, they didn't quite give me enough. Okay, so it starts at 0 and it ends at 0. Halfway in between, it reaches, it goes back to 0, right? Because it's going to go up, down, and back up. So then halfway in between those, it reaches a max, and halfway in between those, it reaches a min. So it's going to go like this. This is the standard sine curve. So then it's going to hit a min, max, or min, 0, max. Okay, standard sine curve in yellow. All right, now we look at the 2, which is going to take all of my x values, divide them by 2. So now instead of finishing a period in 2 pi, it finishes a period in pi, right? So it's going to start at the same place, and instead of ending at 2 pi, it's going to end at pi, right? So halfway in between, it's going to also hit a 0 because our pattern is max, 0, min, 0, max, 0, min, 0, right? So I'm going to go 0, and then I'm going to hit a max halfway in between those 2 zeros. I'm going to hit a min halfway in between those 2 zeros. I'm going to hit a max, 0, min, 0. Okay, so here is what that 2 does to my function. Okay, so it just squishes it in and takes all of my x values, divides them by 2. Okay, now finally our shift, and I'm actually going to do this in red because I don't know that blue is very easy to tell the difference between the blue and the green. Okay, so this takes all of my x values and adds pi over 4 to them. Okay, so it doesn't change the shape of my graph. Remember, this is just a shift, left or right. So instead of right here, now this is going to be here. Instead of here, it's going to be here. Here, they're going to go there, and there's going to move over. It's just a copy and a paste. Literally take the function that already exists, and we just move everything over 1. So our final one is that red one. Let's see if I can erase. Aha! I can at least erase the sine curve that I had there, and then the yellow sine curve. So this is our final curve. It's got a period change, which squished it in, and it's shifted to the right. Okay, so the one identity that you're going to need to remember from pre-calculus, I know you did tons of identities in pre-calc. The one you're absolutely going to have to remember, sine squared plus cosine squared equals 1. Now, if you're going on to Calc 2, you are going to need to know other identities then. So it's not like you totally wasted your time. But just know that here in Calc 1, mostly we're going to use sine squared plus cosine squared equals 1. You have to remember that. You have to know it. You have to be able to just say it in your sleep, okay? So we're going to use the Pythagorean identity to rewrite, because here's the thing. When we're taking trig derivatives, a lot of times we need to rewrite them because we can't take the derivative one way, but we can take the derivative another way. Like, we need them rewritten, so we need to be able to use these. Okay, so the first thing I notice is I've got a cosine and a sine, and so I don't know what to really do with that. So I have sine squared, and so let's just replace sine squared with something that it equals, right? And sine squared theta is going to equal 1 minus cosine squared theta, because I just, that is really ugly, that's not working very well. I just subtracted cosine squared from both sides. So I have 2 cosine theta minus, and I'm going to replace sine squared with this, so I have 1 minus cosine squared theta equals negative 2. Okay, so then let's rearrange this. So this is just 2 cosine theta minus 1 plus cosine squared theta equals negative 2. I add the negative 2 to both sides, and I have 2 cosine theta plus 1 plus cosine squared theta equals 0. And then I noticed something that, normally when we're writing polynomials, we write things with the squared in the front. So let's just do that, because it might not be obvious right now how we can do anything with this to solve for theta. But now maybe it is obvious, because if this was x squared plus 2x plus 1 equals 0, would you know how to solve it? Yeah, you would, right? Because it's just factor. You just factor it. Well, guess what? Cosine squared is the same like that, right? So we're just going to do, this is, to factor this one, it would be x plus 1 squared, right? So in this case, this is just going to be cosine theta plus 1 squared equals 0. And then we take the square root of both sides, and we get cosine theta equals 0, cosine plus 1, sorry, cosine plus 1 equals 0. So then we have cosine theta equals negative 1. And then we look at our unit circle. Where is cosine theta equal to 0? Well, cosine is the y-coordinate, and the only place that it's equal to 0 is at pi, so theta has to equal pi. That would make it true. So then you can use the calculator to verify your solution, put that back in. Speaking of calculators, at the very beginning of this, you might have noticed I just skipped over these calculator ones because I don't really have a really great calculator emulator on my computer yet. I haven't found a good one yet, but so I'm just going to walk you through how you would put this into your calculator, but I don't have a real calculator to show you, which is, it is what it is. It's good. So the very first thing you do is when you walk in, you put it in radians. In calculus, we almost never use degrees. We talk about them in degrees sometimes because they're easier to think about, but really, just switch it into radians, because it happens all the time that people forget to switch it into radians for the calc test, and that's a problem. So switch it into radians, and then you literally just type this in, sine of 2, and it'll spit out a value for you. In fact, it'll spit out 0.909. Okay, tangent of negative pi over 5. Again, you just plug it in. So make sure you use parentheses so that you have negative. You're not taking negative tangent of negative pi and then dividing it by 5. That you're taking tangent of the whole thing. But go ahead and try that, and you should get negative 0.726. Okay, now secant of 1.3, and you're like, but I don't have a secant button. Well, what is secant? Secant is the same as 1 over cosine of x, right? Secant x equals 1 over cosine of x. Okay, so secant of 1/3 would equal 1 over cosine of 1.3, not 1/3, sorry. So you just plug that into your calculator again, and you get 3.738. Okay. Last but not least, we have these. We want to try to find the missing angle, find x. So I know that sine of this angle, which is 0.5, equals opposite over hypotenuse. So then I have x sine of 0.5 equals 5, and I divide both sides by sine of 0.5. And so then in your calculator, you just do 5 divided by sine of 0.5, and you get your answer. Okay, last one. So I have an opposite and I have an adjacent. So I do tangent of theta equals 2 over 5. So how do I undo the tangent? I do the inverse tangent, and you have a button for that. So we do inverse tangent of 2/5 equals theta. And that's all for trig. Well, until calculus.